Here we're going to cover the birth of quantum mechanics. As we saw with relativity, we discovered problems with our current theories about electricity and magnetism. And we're going to run into the same problem here with the black body, the attempt to explain why hot objects give off thermal radiation. And we'll see this led to us quantizing the energy given off by black body, what we now know are photons, and this was done by Planck. So in any case, if we take a look at the history of quantum mechanics, again, it did start, although there are a lot of other problems that were occurring at the same time, but it did seem to start with blackbody radiation and trying to understand why different objects would radiate this thermal energy. It was confirmed by the photoelectric effect, which really built on the results of Planck's work, and was confirmed by Einstein. And then, of course, atomic spectra also played a very big role in understanding the quantized energy levels in an atom. So basically, with quantum mechanics, we can't point to one individual who's responsible for developing quantum mechanics, but rather it was a large number of physicists, and Einstein was in there too, who made significant contributions to our understanding. So black body, what do we mean by a black body? Well, the ideal thermal radiator is an object that would appear to be dark. In fact, a perfect black body would have no reflectivity whatsoever. And we can see thermal radiation in the case of incandescence. For instance, a hot filament, a hot tungsten filament in an incandescent light bulb glows because as we send electricity through it, it heats up to a very high temperature. And as a result, most of the radiation that it gives off, most of the electromagnetic radiation given off, is in the form of infrared light, making these lights very inefficient. But a significant amount of energy is given off in the form of visible light. We also see this in just about anything which is, above about 1,000 degrees Kelvin. Once we get above that level, we're getting into the realm where temperatures are high enough, where there's enough visible light that we can actually see it. And hot coals, for instance, are a very good example of something hot enough to generate visible light. Most of the energy is still infrared. If you put your hands in front of hot coals, you could feel the infrared radiation. But there's a high enough temperature there to actually see the visible part of the thermal radiation. So starting with John Tyndall in 1864, John Tyndall ran an experiment where he measured the thermal radiation from a hot platinum wire. Platinum has a very high melting temperature. And essentially what he did is send electricity through this, and at different temperatures measured the amount of thermal power that was coming off of that filament. And Joseph Stefan was able to use these results and to demonstrate that the amount of thermal power was proportional to the temperature to the fourth power. So this led to Stefan's law of thermal radiation. It was confirmed by Boltzmann, so sometimes we call this the Stefan-Boltzmann law. But it basically says that the power given off by any thermal radiator, anything that is hot, will go by this constant right here, which is 5.6696 times 10 to the minus 8, sometimes called Stefan's constant. A is the surface area of the object during the radiation. Obviously, with more surface area, it's going to give off more radiation. E is something called emissivity. And this isn't the most intuitive thing to understand, but the darker the object is, the more it will radiate. So, for instance, if something reflects very, very little light, it will tend to radiate the most thermal radiation. Whereas if something is very reflective, nearly 100% reflective, there won't be modes available to radiate this thermal energy. Now, most importantly, this power is proportional to the temperature to the fourth power. So we don't need to increase the temperature very much to have the radiative power increase rapidly. So, you just do the math. 2 to the fourth power is 16. So if you double the temperature, and this is absolute temperature, so you're not using Celsius or Fahrenheit, you have to use Kelvin here. But if you double the temperature, the radiative power goes up by a factor of 16. So again, an ideal absorber, something that was very, very dark. We can't theoretically reach 100% absorption or a perfect black body, but we've come pretty close with some materials. And the ideal absorber would actually be the ideal thermal radiator. It would radiate the most amount of electromagnetic radiation due to this heat. And again, we would refer to this as a black body. If we go to the other extreme, we can actually, if we could create this, an object that is perfectly reflective in all parts of the electromagnetic spectrum would never radiate off any heat, which is interesting. If we could hold something like this in a vacuum, we could keep it hot indefinitely if we didn't have it in contact with anything that could take the thermal energy. But of course, nothing like that exists. Even the most reflective surfaces do radiate some energy. They're not 100% reflective, so we never get an emissivity completely down to zero. But in any case, this Stefan's law, or the Stefan-Boltzmann law, is very, very important because it basically explains how different objects behave as they radiate at different temperatures. And if an object is in thermal equilibrium with its surrounding, the power that it radiates will go by this first term right here, which is sigma A E times its own temperature to the fourth power. But of course, we have to take into account that the surroundings of this object are also going to radiate. So the net power that they give off would also have to include the energy which is being absorbed. So obviously, if you're warmer than your surroundings, you're going to radiate energy into the environment. We are warmer than our surroundings oftentimes, so we are constantly dumping energy into the environment. However, if our environment is warmer than we are, the net power will be toward us, so we will give off a negative net power because we're gaining power, I should say. In looking at thermal radiation, we notice that when something is very cold, it's not radiating very much thermal energy. Most of that energy is in the infrared, but as it gets warmer and warmer, it tends to go from a deep red to a orange to a yellow, and in the most extreme cases, it will actually become white hot or even have a bluish color to it. You can't watch welding take place. You're supposed to protect your eyes because of the ultraviolet light. But at welding temperatures, the light will actually appear to be bluish. So experimentally, this was studied, or I should say these colors were studied. The peak wavelength was studied by somebody by the name of Wilhelm Wien. And he discovered what we already know, that the color of these objects will change as a function of temperature, but the middle wavelength, because honestly, this is a spread of different wavelengths which is being radiated, the peak wavelength will be inversely proportional to the absolute temperature. And this displacement law showed that as we go from 2000 to 3000 degrees Kelvin, we know by Stefan's law, we're going to radiate much more energy because it's 1.5 raised to the fourth power. Okay, so the total power is going to be much higher. But also, we get a shift in the wavelengths which are being radiated. We get a shift to shorter wavelengths. The wavelength is inversely proportional to the temperature. As the temperature goes higher, the wavelength gets shorter. So at 3000 degrees Kelvin, we've gone from something that barely radiates in the visible spectrum, maybe giving off a little bit of red light, to something that's more orange in color, okay? At 4000 degrees Kelvin, a little more yellow, and of course, at 5 to 6000 degrees Kelvin, where our sun is, it will radiate right in the middle of the spectrum and appear to be this sort of yellowish white. And Wien was able to actually make this argument based on thermodynamics. So again, relying on classical mechanics or classical physics to come up with this, we're still not getting too much of a problem. And this was done in 1893. Here's where the problem comes into play. Well, we'll get to that in just a second. But again, Wien's displacement law has our wavelength dependent inversely on the temperature. So as something gets hotter, obviously we go to shorter and shorter wavelengths. Now, looking at Wien's displacement law, this wavelength here represents the peak wavelength. So you have to go to really, really cold temperatures where there's almost no thermal radiation. The power is very, very low, pretty much undetectable. So the temperature of 0.001 Kelvin at 1 millikelvin, the peak wavelength would be 2.898. That should be centimeters, and that's in the radio part of the spectrum. At a temperature of 0.1 degrees Kelvin, we're starting to get into the microwave. The blackbody radiation of the Earth is the blackbody radiation of the Big Bang, the cosmic background radiation, is actually around 2 degrees Kelvin. So that would also be in the microwave. Let's jump up a little bit. Our body temperature is around 300 degrees Kelvin. So we radiate right around 10 microns. We can't see that because that's in the mid-infrared. Going higher, we get to peak temperature still in the infrared, but around 1000 degrees Kelvin, you've shifted the whole radiation curve far enough toward the visible that even though it peaks somewhere around 2.9 microns, we're starting to see some red light at these temperatures. And again, at 2000 degrees Kelvin, we're right on the edge, near infrared, and 5000 degrees Kelvin, which is, our sun's a little bit warmer than that. You're getting into the visible part of the spectrum, okay? So at the temperature of the sun, which is sometimes quoted around 5600 degrees Kelvin, you would be, right around yellow light. At 10,000 degrees Kelvin, the peak actually shifts to just on the edge of visible and ultraviolet. Would appear to be, very white to us, to our eyes, albeit maybe a little bit bluish. 20,000 degrees Kelvin would definitely have sort of a blue-white tinge to it. But obviously, at these two peak wavelengths, we'd be getting a lot of ultraviolet light, so it wouldn't be safe to look at anymore. So again, when we weld, we're normally in these temperatures right here, which gives off a lot of ultraviolet light, which means you need to shield your eyes. At 1 million degrees Kelvin, which is, the temperature of parts of the solar corona, it's giving off a lot of ultraviolet and X-rays. And at 1 billion, technically there's still X-rays, but at 1 billion degrees Kelvin, although I guess you get some thermal radiation also from the nuclei, you'd be in the gamma ray part of the spectrum. So here's sort of what it looks like. I've changed from a previous scale. This is a linear scale where we're looking at the radiation intensity. It's arbitrary units on the left. You can see the form that it takes on a logarithmic scale. Both logarithmic in wavelength and relative intensity. It looks something like that. But you can see here's Wien's displacement law as we're moving off to the left, and because it's logarithmic, if we graph 1 over t, we will get a straight line on a logarithmic graph. But you can clearly see as we're moving to higher and higher temperatures, that peak light is going from the infrared to the visible. Now, as far as stars, you look at the nighttime sky, and for the brightest stars, we can actually see a bit of color. Color is difficult for our eyes to detect when light is very, very low, because our cones, which are responsible for color vision, are not as sensitive. But if you look at the constellation Orion, Orion is a great example because in it we have a red supergiant, Betelgeuse, and we have a blue-white supergiant, that's Rigel. And there's also a blue star, Mintaka, and it's also a supergiant. It's actually further away than the other two stars. But all of these demonstrate this concept that as the temperature shifts, the wavelength of the light also shifts. So from the very bottom, M-class stars are the coolest stars at 3,000 degrees Kelvin. That is, pretty close to where Betelgeuse is. And then Mintaka is up around 40,000 degrees Kelvin. So it has a very distinct blue color to it. In fact, if you look at other stars, such as Alpha Centauri, it's hard to see in this photograph right here. Alpha Centauri definitely has a yellowish color to it. Our sun has a yellowish color to it. I would say they appear more white with a yellow tinge to them. But these are two of the closest stars to us, which are visible to the naked eye. Obviously, the sun's very visible to the naked eye. Proxima Centauri is closer to us, but it's not visible. But again, both of these are examples of yellow stars, which are, right sort of in the middle of the spectrum. They're between being a blue star and a red star. And again, if you look at the different, unfortunately, temperatures are somewhat blocked by my video. But if you look at the luminosity of the different stars and their temperatures, these are stars in the main sequence. Betelgeuse is a little bit different because it's a supergiant. Its atmosphere is expanded and cooled, so it's much brighter than it would be during most of its life. It's sort of reached the end of its life. But you can clearly see that the luminosity increases dramatically as the temperature goes up, even though the radius doesn't necessarily increase so quickly. In fact, if you take the luminosity divided by the area, you can clearly see that taking the size of the star out of the equation, temperature has a very dominant role in determining which stars are bright and which stars are not. Most of the stars in our galaxy, in fact, are very dim red dwarfs. In fact, they're so dim, Proxima Centauri, which is the closest star to us beyond our sun, is magnitude 15. I think it's magnitude, I'm not going to quote magnitudes, but you actually need a telescope in order to see it. Now, here's where we come to the problem. And when we find problems in physics, that's where interesting things happen. And there was an attempt to try to understand this thermal radiation. Obviously, Stefan was able to demonstrate that the temperature, the power went by the temperature to the fourth power. Wien did make some thermodynamic arguments from classical physics as to why the wavelength should shift. But the overall spectrum of these black bodies was difficult to understand. And the first attempt to try to, match the spectrum, and that's what we try to do in science. We try to match our results, our experimental results, what is reality, to our theory. We try to match our theory to reality. And Rayleigh genes were not so successful on their first go-around. Lord Rayleigh, of course, was responsible for explaining why the sky is blue. And Rayleigh scattering showed that shorter wavelengths tend to be scattered more easily than longer wavelengths. And in this approach, the way that they used this black body is they actually used a cavity, okay, basically a thermal cavity. They would heat this cavity and look at the light that would come through there. And the reason why they did this is because it replicated a perfect black body as close as they could get to it. Remember, a black body would absorb all the light that would be incident on it by creating this cavity. Even if the light wasn't absorbed on the first reflection, it would be perhaps absorbed later on in subsequent reflections. So they came up with a intensity dependence, which was, obviously depending on the temperature, also dependent on the frequency of the light. That's new. That is the frequency. But when we look at this, we see that there's a problem as we go to higher and higher frequencies. The intensity blows up and produces what's called the ultraviolet catastrophe. Now, the approach that was used here was successful in trying to determine the heat capacities of different materials, specific heat capacities of different materials. It's called the equipartition theorem. And it says, all right, you've got a system with different degrees of freedom. So for instance, if you wanted to find the heat capacity of molecules, what you would do is you would put some of the energy in terms of translational energy, some of the energy in terms of vibrational energy, some of the energy in terms of rotational energy. You would spread it out equally, equal partition or equipartition. And they tried to do that with the different radiation modes of this cavity. And if you think about this, you're basically treating the light as a wave, which will reflect off the interior of this. And this is the cavities that they're using. They use something with conductivity, so the electric field had to be zero inside the conductor. So we would get standing waves, which would fit inside here, and it worked very well for low frequencies. But as we go to higher and higher modes, there actually become more modes per frequency. And the effect that has is, as you have more modes available to you at higher and higher energies, well, you're going to get more intensity at those energies. and that caused the Rayleigh-Jeans equation to basically blow up. So again, you look at this, shorter wavelengths correspond to higher energies. So, from right to left, we're going to higher energies. And the Rayleigh-Jeans work well for low frequencies, where we're looking at the lowest modes in this cavity, but higher frequencies, it would blow up. And that's not unexpected because, quite honestly, if you're using this idea of these cavity modes, you have perhaps you would have an infinite number of standing waves in there. Now, if you're looking at standing waves on a string, usually the lowest modes have the highest amplitude. And as you go to a higher mode, the amplitude goes down. So with this equipartition theorem, you're not doing that. So it creates what's called the ultraviolet catastrophe, because at shorter wavelengths, which would be ultraviolet, it just doesn't work. That essentially, in the classical limit, the oscillators producing these electromagnetic waves would radiate an infinite amount of energy. And of course, they don't have an infinite amount of energy available to them. So in 1900, Max Planck tried to address this problem. And again, he's not a big fan of some of the theories that were out there, such as the atomic theory of matter. Going back at that time, there's still some controversy as to whether that was true. So this concept of these microscopic oscillators was a little bit tough for him to stomach. But the way that he approached this was, he said, look, if we limit these oscillators as to what they can radiate, we can perhaps correct some of this high frequency problem. And again, Rayleigh-Jeans worked well for lower frequencies, but he had to come up with something that would bring this whole thing back. We have this frequency squared dependence of Rayleigh-Jeans. We needed something to sort of bring this whole curve back, so that at the highest energies of electromagnetic radiation, we would not have this intensity blowing up on us. So again, here's the way that Planck sort of thought about this whole system, that all of these little oscillators, which were in the walls of this cavity, they'd be giving off packets of energy. Okay, where this is going, quanta. You give off quanta of energy. And really, the oscillators were restricted in terms of the vibrational modes that they could have. This is really trying to cure this big high frequency problem that we were running into. And he basically said that, okay, these little oscillators can have energies of some integer n times some very, very small number. He thought that this number was going to go away when he tried to match the experimental value. H would sort of go to 0 times the frequency. Sorry for switching from nu to F. I'm bad about that. But in any case, these quanta of energy being given off would basically be fixed. So if you went to a very, very high frequency, they would be spread out. Because again, I guess the best way to explain this is, as you go to higher and higher frequencies, the difference in energy between each subsequent mode would get closer and closer and closer. You just have an enormous number of these high energy modes, which you're throwing your energy into. Now everything's equally spaced. And the effect that this had was it tamed the whole equation, as opposed to this, which would clearly blow up by quantizing the energies. That created this new term right here. And again, we see that here we have KT, K being the Boltzmann constant, T being the temperature. And by quantizing the energies, we got this form right here, where again, H was a very, very small number. I did it again. I switched from F to nu. And here you can see that temperature was contained in this right here. Now, when temperature became very, very large, this exponent here would become very, very small. And, we would always basically keep the U being the amount of energy per unit area. That would bring this whole equation back to zero. Okay, so as I should say, as the frequency went to infinity here, this equation would basically come down to zero. So Planck really unwittingly invented the concept of this quanta. He did this as sort of an ad hoc, correction to what Rayleigh-Jeans had done, just to, make the system behave. And while Planck, struggled with this and sort of put this away, went on to work on other things, Einstein saw this and he saw the genius of this. He said, wow, this shows that this electromagnetic energy, these electromagnetic waves really come in these packets, these quanta, which we now know today to be the photon. And as a result, Planck, for his little ad hoc fix, won the Nobel Prize in 1918. So that is really the beginning of quantum mechanics. And as we're going to see, this existence of the quanta, this existence of the photon, is later tested with the photoelectric effect. So there we go.